The first and perhaps most important thing that we need to do in any data science exercise is to discover what the problem is. And I'll start by telling you why this is important. Then we'll be looking at how you can go about this. In this module, I'll be giving you some simple tools on how you can go about discovering the problem. These take the form of templates rather than software, but is still perhaps the most critical step that you can take in any exercise. Let me start with a real life situation. We were predicting viscose price for a commodities company. And the president of this company gave us a straightforward exercise. He said, I have viscose price. I have the price of several other things like the raw materials, the competitors, I have economic indicators, and so on. I'll give you all of this information and I would like you to predict viscose price for me. So we did this. It was a 3 month engagement, and around 9 weeks into this engagement, fairly close to the end, we shared with him the results, which were pretty good actually. What we'd done was we'd taken the original data and then we had some missing values in the data. So on some days the data is not available either because it wasn't traded or because the data was not collected. So we made sure that we fit all of those imputed values and there were no missing values in this. We then looked at what are the variables that can actually impact the price of viscose. So for example, does the downstream substitute price uh, specifically of polyester yarn index make a difference? Do competitors' prices make a difference? Do substitute prices make a difference, or the indices? Do economic variables make a difference, and so on? We looked at this in two ways. One is causality. That is, if there is a change in the price of one of these variables, does it explicitly in the future cause a change in the variable that we are looking at, which is viscose price? Second is there a correlation, meaning when the other way, that is, if any of these variables are any of these variables affected by the price of viscose itself? And while the correlation is high in a reasonable number of cases, causality was strong primarily in one case, but certainly there were a whole series of variables, potentially up to 18, that seemed to have at least a reasonable effect. And then there were some that we said, even though they have a low effect, let's include them because the model certainly can improve. So, in other words, there were 16 strong influencers, 2 moderate influencers, 8 unknown influencers, and we use this as part of the modeling exercise. Overall, instead of building one model, we built 9 models. We found that different models have different accuracies for different time periods. So we took an approach that combined these models. And overall, the vector error correction model, for instance, had a pretty good accuracy, 96%. Autoregression was only slightly further behind. Neural networks were only slightly further behind. But on average, they were giving something in the order of 96%. But even linear regression was giving some reasonably good results. 93.6 is not bad at all, but we said let's just keep it to these kinds of models. And we presented these results at that particular point in time. Now, we were pretty happy. We said, look, 96%, I mean, that's solid accuracy, right? And we also showed him that with the vector error correction model, this is the kind of spread that you would get. The errors, for example, when we predicted it 2 weeks ago, or sorry, 4 weeks ago, was only 1.3%. The error 2 weeks ago was only 1.1%, and so on. So the errors are well within the bounds, even as we were running it in real time. So we were expecting to get a pat on the back. The president said, gentlemen, viscose price only varies by 1.5% over a week. If you are going to tell me that you have a model with 96% accuracy, plus or minus 2%, well, in this case, maybe even worse than that, that's of no use. I can't make any decision based on that. My colleague and I were looking at each other and we said, oh shit, we've lost this case, haven't we? Here's the thing, what we missed was something the president added just a little bit later. He said, maybe I haven't explained and my team hasn't explained what we are going to do with this. So let me do that. He said, what we are going to do is if the price of viscose is going to go up, then we will hold inventory. We won't push it in the market. By just waiting for a week, it will sell for a slightly higher price. And that is good for us. But if the price is going to go down, then we would rather dump as much inventory as we can and get the higher price. So he said, maybe your model is not doing so well because it's trying to predict the exact price. Will it help? He asked. If I asked you not to predict the price, but just tell me if it's going to go up or down, because that's the only information that I need to make a decision. We were stunned. What he'd done was changed what was a forecasting problem into a classification problem, completely changing our approach. We did go back. We managed to finish that engagement in the remaining 3 weeks and come up with a classification model that had close to an 80% accuracy. And that was great because what he's able to do now is 4 times out of 5 figure out whether the price is going to rise or fall. Whereas earlier, at best, they were able to do it only a little over 50%. But we made a mistake because we did not really discover the problem. And what I'm about to do is give you a simple tool set that will help you discover what the real problem is before you start solving the problem.